if you just zoom in on prediction, which is the thing we sort of know how to talk about, even just if you just consider yourself like a passive observer trying to do prediction, even then, all of our technology is sort of proceeding on a very naive assumption, which is that basically you're going to go and there is some distribution. We call it like the distribution. Like there actually is this fixed distribution that, you know, God knows, but we don't, and that we have some procedure to collect samples which are, you know, drawn from this probability distribution, and that the data that we have seen has been collected by drawing a bunch of samples completely independently from this fixed underlying distribution. And then the data that will encounter at deployment time will also be created by drawing more examples also independently from the same underlying distribution. And the problem there is that that's just not how the world works. If you train on I don't know, you're trying to train some text classifier based on Twitter data up through 2016, and then you're deploying it on data past 2016, people are talking about different topics. And hopefully again in 2021, we'll get to talk about different topics. People will use language differently. There will be slang that wasn't there before. So there will be a shift in distribution over inputs that we're encountering, and it's occurring in a kind of haphazard way. You know, you have like gradual changes in the use of language. You have sudden changes in the sort of like emergence of topics. You know, the fact that like, you know, overnight everyone's talking about COVID, you know, 20% of the time, which just never happened before March 2020. And in these cases, there's a question like, what can we do? How can we make valid predictions, or how can we have some kind of faith in the reliability of the predictive technology that we have, even if we're just focusing on prediction, when we're faced with this kind of dynamic environments? And I mean, even in a setting where there's no feedback loop and we're not worried about decisions. And the answer is that this is in general impossible. So basically, if we assume nothing about the way that the world can change, we actually are always acting under some amount of ignorance. If anything could change in any way, there's no reason to believe that if we can make no assumptions about the way that the historical data is representative of the data that we will see in the future, all bets are off. Technically, there's sort of a few different paths forward. And one is that we actually can make technical progress on this problem of learning when the data distribution is shifting, if we can make some assumptions. We don't have to assume that everything is exactly the same, or there's some fixed underlying distribution. But we can make certain types of assumptions like, okay, the frequency of the categories that I'm trying to predict are changing, but what the instances look like, the distribution over instances given the category are relatively the same. So an example would be like a disease, like say COVID is trending up and down, and I might want to track, you know, what's the frequency of COVID in the moment. And if I believe that what COVID looks like in terms of its manifestation and symptoms is not changing in the short term, but the prevalence or the incidence of the disease is changing dramatically in the short term, then I can sort of, using this structural assumption, develop some, you know, reasonably elegant machinery around it to leverage this invariance. Say, okay, now I can actually identify this parameter of what is the incidence in the moment. So I can assume this kind of like invariance of a conditional probability, like the symptoms given the disease aren't changing, but the prevalence of the disease is changing. You could also sometimes find scenarios where you could work with the opposite assumption, that the distribution over the inputs is changing, but you believe that the probability of, like, say, the disease given the symptoms is not changing, or disease is a bad example, but the category given the inputs is not changing. I'd point out, though, that this requires some prior knowledge. You need to know which assumption applies. And if you make the wrong assumption, you'll come to the wrong conclusions. So this is like a common thread through like causal inference. And I know Christian's done a lot of great work in applied causal inference in the context of criminal justice. There's sort of a basic tenet that like data plus assumptions can lead to sort of causal identification of like parameters of interest, but the data often alone is insufficient to tell you which assumptions are valid. And if you make different assumptions, you'll come to different conclusions. So these might be things you need to experimentally validate. I'll give a simple example. Is people often assume when they deal with shifting data distributions that probability of y given x, the probability of the label given the inputs, is not changing. This is invariant. And the easy counterexample is, imagine that you're looking at symptoms data and the only feature that you have is cough, and the label of interest is coronavirus. If you look in December 2019, probability of coronavirus given cough is about 0%. Now in the future, all that's changed, say, is the amount of coronavirus, but now probability of coronavirus given cough is maybe quite high. Maybe it's 5% or something. So you get the idea. is that these are very hard problems, and you sort of have two worlds. You can make some kind of assumption about like either there's some kind of invariance in the conditional probabilities, or you can assume something about smoothness, that the distribution is changing, but it's changing only very gradually. And I could assume that like between any two nearby time periods, the divergence in the distributions is limited. There's something I could do. Then you have the world of deep learning, which some of you might have seen, in the world in which I grew up academically, which is the world of training large-scale neural networks, which has thrived largely on an ethos of like, try shit and see what happens. And this is very effective when you have just a well-defined supervised learning goal. You assume no distribution shift, and you basically say, hey, I'm going to get to verify if the model worked on holdout data, so I can license you to just try whatever you want and see if it works. And people have tried sort of using that mindset of let's just try stuff and see what it works to approach hard problems of distribution shift. And they'll sort of say, okay, I have domain A and I have domain B, and they're sort of different from each other. I'm going to throw spaghetti at the wall and see what works. The problem here is that, they're trying 9 million methods, and they only have like 3 different data sets. And they realize that now the relevant effective data size is not the number of examples you have in each data set, but the number of instances of shift that you've seen. And just because you find one method that like you trained it on like handwritten digits, and then it worked well on like colored handwritten digits, doesn't mean that this is going to work to other kinds of shift.